Today, we're going to start a new chapter on moments. And you have seen moments before. In physics, you probably called a moment a torque. So, moments are also called torques. Let me draw a quick picture. I think the easiest way to conceptualize moments and torques is to actually go pick up a wrench. So, let's say you had a wheel on your car and you need to change the tire. It has maybe these 5 lug nuts on it. And let's say you're finished changing it, you're putting the new one back on and you need to tighten it. Well, you're going to put some kind of a wrench on here that goes out some distance away, and you apply a downward force F to that wrench. And in doing that, your goal is not to push the tire down. Your goal in applying that force is to cause rotation of that lug nut about an axis coming out of the page toward us. We call that a torque. The idea is we need this distance. This dimension D right here is crucial for figuring out how big the torque is. And if you need to apply a really big torque, you're limited to how much force you can apply. Sometimes you'll want to get a longer and longer bar because the farther out here you apply the force, the bigger the torque. Okay, we're going to not use the word torque very often in this class. We're going to use the word moment instead, but it's the exact same idea. A moment is caused by a force a distance away from a specific point, and specifically, we want to find that perpendicular distance to calculate the torque. How are we going to use this? Well, you guys remember Newton has some laws of motion. The one we've been using so far this semester is the force equilibrium equations. It's a simplification of Newton's laws of motion for when we have no acceleration. And that is definitely required for something to be in equilibrium. But then we also, in order for something to be in equilibrium, we have to require that all of the torques, but I want you to get used to using the word moments instead, all of the moments have also got to sum to 0. Because if you have an unbalanced moment on something, it's going to start rotating or spinning. And in physics class, you might have calculated angular acceleration. We're not going to do any acceleration here because we're dealing with statics. So to solve for that moment in 2 dimensions, we'll oftentimes just write it as F times D if D is a perpendicular distance. We will talk in a minute about what we're going to do when we don't know the perpendicular distance. But because of that, we're going to end up with units for moments and torques of force times distance. So either newtons times meters or pounds times inches or feet. Make sure you have both a force and a length in there. And when we talk about the direction of a moment in 2 dimensions, we'll call it clockwise or we'll call it counterclockwise. And I'm fine if you use the CW and CCW abbreviations for clockwise and counterclockwise, or you can draw these little curly arrows. So in 2D, we're typically going to do clockwise and counterclockwise for our moment directions. One way to think of this is if I have a coordinate axis with an X and a Y direction in 2 dimensions, counterclockwise, let me draw counterclockwise on here. Counterclockwise would be rotating that way. And if we're going to end up using the right hand rule, so the way we use the right hand rule in this class is if you curl your hand so that your fingers are heading that direction, your right thumb will be pointed straight out of the page at you. For a moment that's counterclockwise, points out of the page at you. And out of the page for X, Y, and Z, right-handed coordinate system, that's in the positive Z direction. So we're typically going to call counterclockwise a positive moment. Just like we usually call a force that acts in the positive X direction a positive force, this moment is rotating about the positive Z direction, sticking straight out of the page at us, so we're going to call that a positive moment. Okay, we are going to need to do these in 3D in general. Let me draw a 3D coordinate system here, where we can put the X and the Y down in the horizontal plane and the Z coming up at us. Well, if I have a force, let's draw my force vector, say it's somewhere over here, and I want to find the moment it causes about a point, like the origin, I need a position vector that gets me from the origin to the force. And it would be really fantastic if I could find the perpendicular distance, but usually that's not so easy. So instead, what we're going to do is just grab any position vector that's convenient that goes from the point where we're finding the moment to our force vector F. And it turns out it can be any position vector that goes from the point where we're finding the moment to any location along F. So I could actually have R go down here instead. It can go to any point along there. And then what we can do is we can calculate the moment as a vector by using the cross product of R cross F. This is using a vector cross product. And a little bit later, I'm going to remind you how to calculate these, and we're going to get lots of practice with it. What if R and F were parallel? Well, if R and F are parallel, do you remember what happens if you take the cross product of two parallel vectors? Well, R cross F is 0. If they were parallel, you're going to get no moment. First, though, we're going to start with 2D, because in 2D, that cross product simplifies down quite a bit. Make a position vector. So here's my point. There is my position vector, and then maybe I have a force vector that's off in a different direction, so they're not parallel. And if I wanted to find R cross F, I'm going to end up with a vector that is pointed in the Z direction. If your R and F are both in the XY plane, your actual moment, what results when you take the cross product, is a vector pointing out of the plane in the Z direction, right? Think right-hand rule. So if it tends to cause a rotation that way, the moment vector has a direction that is your thumb pointed straight out of the page at you. If it happened to be clockwise, your thumb would be pointed straight into the page from right-hand rule. So we usually in 2D, since they're all of our moments are going to be about the Z-axis, we typically just want to find the magnitude. And we can calculate the magnitude using a nice formula you may have used in physics, where we just take the length of R times the magnitude of the force vector F times sine of theta. And theta, there's two different ways you could define theta here. You could either define theta using this side, maybe call it theta 1, or using that angle, call it theta 2. So we have two different angles that we can use as theta. And it turns out I have an angle and I find the sine, and then I have 180 degrees minus the angle, or it's supplement, and I find the sine, you get the same number. With cosine, you get an opposite. One would be positive, one would be negative. But with the sine function, we'll actually get the same answer. So here we can use either theta 1 or theta 2, and this is going to give us the magnitude of our moment vector. I want to remind you that moments are vectors. We tend to think of it as rotation about a particular axis. So in 3D, I could draw a moment vector this way, and our book does tend to sometimes use this double-headed arrow at the end of a moment vector. What I'm going to usually draw them this way, with both a curly thing and a double-headed arrow. The double-headed arrow means take your right thumb and point it in that direction. And then the sense of rotation is the way that your fingers would then curl around that purple line. That's how you're rotating. So if this is the direction that our moment is acting about some weird axis, well, just like with force vectors, we can break this up into a Z component, a Y component, and into an X component. This would be the component of the moment about the Y axis, component of the moment about the Z axis, and the component of the moment about the X axis. So that means we'll be able to write moment vectors as an X component that is causing rotation about the X axis, plus a Y component times J, plus a Z component times K. The way we're actually going to calculate it using the cross product is like this. We'll have R cross F, and then I like to put this inside of a determinant, and then we'll put down the X, the Y, and Z components of our first vector, which will always be the position vector, and then our second vector, which will always be the force vector. Remember, with cross products, the order matters. You cannot flip the order of R and F, or you will get the wrong answer. In fact, your answer will be exactly the negative of what you should get. What you get if you actually work that out is the moment vector is going to have an X component, Ry times Fz minus Rz times Fy. The second one becomes RZFX minus RXFZJ. And finally, RXFY minus RYFXK. So this first piece is your moment about the x-axis. The second piece is your moment about the y-axis. And this third piece is, we call it the moment about the z-axis. They really are just the components of that moment vector. And when we go to do equilibrium equations, we're going to take all of these moments about the x-axis, add them up, and set them equal to 0. All of these y moments and add them up, set them equal to 0, and all of these z ones, set them equal to 0. I want to talk just a second and show you that this is the complicated 3D case, but this simplified two-dimensional case is actually hiding in here. In 2 dimensions, you would not have any force components or R components in the z direction. So you will not have any moments about the x-axis or any moments about the y-axis when you're dealing with a 2-dimensional problem. You will actually only end up with moments about the z-axis. And what that means is that my 2D picture up here, this R and this F is going to tend to cause to rotate my part not spinning about an x-axis here in the plane, and it's not going to cause it to spin about a y-axis here in the plane. It's going to tend to cause rotation in the plane, which by the right-hand rule means you're actually rotating about a z-axis. And there's the equation you'd end up with, rx times fy minus ry times ff. So you're just combining x and y position vector components with y and x force vector components to figure out the rotation on the z-axis. We now need to actually go find moments. So there are 4 different ways I know to find moments, and I like to use whichever is the easiest for the specific problem. First up, we can always take the force times the perpendicular distance if we can figure out or we know the perpendicular distance. Second, in 2 dimensions, we can use RF sine theta if the trig isn't too bad to figure out theta. But these 2 really only work well in 2D. The one I use probably the very most often is components. This one will work for any 2D and any 3D problem. What I mean by components is if you get all your force vectors into x, y, and z components, and then you find all your distances in the x, y, and z direction, you basically are using F times D for every force component and every distance that you need. So it lets you find perpendicular distances so you aren't having to deal with sine theta. And then finally, you can just take the actual vector cross product. This one is best for 3D and complex problems. Okay, so we're going to practice all of these. I think when we first get started with 3D problems, you're all going to prefer using the cross product. And then as you get better at starting to visualize these, you might start to prefer vector components. Really, either one will work for any 3-dimensional problem. So let's start with a 2D example. Here we have a couple of workers that are exerting different forces. One of them is applying a force of 80 pounds, F, over here. The other one's applying a force of 50 pounds up here, right there. And they first want us to find the moment of each force about point A down here. And then they want to find out which way will the pole rotate with these guys pulling with 80 and 50 pounds. Will it want to rotate clockwise or will it want to rotate counterclockwise? So basically we're going to figure out the moment each force causes about A, figure out which one is bigger, and that's going to tell us which way it's going to rotate. Let's start with that 80 pound first. The 80 pound force, well, we can always use RF sine theta if we can figure out the theta. And it looks like the theta is going to be pretty easy to figure out. The 80 pound force, let's draw it on here so I make sure I use the right one. I would need an R that goes from A to the force. There's my R. So R is going to be 12 feet. And then my force is 80 pounds. And then I need the sine of theta. How am I going to get the sine of theta? Well, the theta is this easiest to use is this one right here. And that angle matches this angle on my little 3, 4, 5 triangle. So to get the sine of this little angle, which is the same as that angle, sine is opposite over hypotenuse. So I'm going to use the opposite side, 4 over the hypotenuse, 5. 4 over 5 is the sine of the angle. And you multiply that out, you get 768 pound-feet. And that is going to be rotating this way, which is the same way the clock turns clockwise. So that's a really fast way to find it. You do have to figure out which of these angles you're using and how to get the sine of theta. So you could alternatively figure this out using components. I want to practice this because I use it way more often than I use RF sine theta. So the way we do it with components is first I need to take that force and break it up into its x component and its y component. Well, this x component, I'm going to use this horizontal side over the hypotenuse of that little triangle is going to be 4/5 of 80 pounds. And the y component would be 3/5 of 80 pounds. So just taking that 80 pounds and splitting it up into x and y components, I'll just draw them on the picture. Now to figure out the moment that force causes about point A, I already know the perpendicular distance of each of those force components from point A. I will end up with the 4/5 times 80 pounds, that's the x component, times, and it should be a y distance, and it should be a perpendicular distance. Well, the perpendicular distance is just 12 feet. So this is like your fx times your ry. Now, what about the other component? What about this vertical 3/5 component? Well, I could also try to include it. 3/5 times 80 pounds is your Fy. And now I need to know this force right here, what is its perpendicular distance from point A? And I have an awful lot of students doing this early on that will try to grab that 12 feet, but that is not a perpendicular distance. This force, think about it as living on a line of action that goes forever. Do you see that its line of action goes right through point A? So that means that this force will not cause the part to rotate about point A because there's no x distance. In order for this force to cause the part to rotate about point A, it would need to be shifted over here to the right or over here to the left. It would need a perpendicular distance away. So anytime a force is directed right at a point, it does not cause a moment at that point. So you multiply this by 0 feet, which is your Rx. And you do that math and you get, no surprise, 768 pound-feet. And it's still clockwise. Okay, let's do the 50-pound force. So if we want to start with RF sine theta, well, R this time is we're gonna go all the way from A all the way up to P. Remember, P is 50 pounds. So R is now going to be our 12 feet that we had plus 6 more feet. So we'll use our 18-foot distance. The force is 50 pounds. And then I would need sine of theta. And we're given that this triangle is 45 there. So this theta right here would also be 45 degrees. And we multiply that out and we get 636 pound-feet. And that one's going to tend to cause counterclockwise rotation. Should we do that one with components as well? So to do components, what I want to do is first split P up into a horizontal. 50 pounds, I would probably say cosine 45 because it's the horizontal component and the horizontal is adjacent to the 45 that's given. And then this one right here, the downward would be 50 pounds sine of 45 degrees. Whether you call them sine or cosine depends on whether you're using this angle or this angle up here. And since they're both 45, you're going to get the same answer. So I was using this angle down here, which says that the vertical side is opposite the 45. So that's why I use sine, and the horizontal side of the triangle. So the horizontal component is adjacent. So I used cosine. The X force is the 50 pounds cosine 45, and that gets multiplied by the Y distance, which is this whole 18-foot distance. Then I would also have the 50 pounds sine of 45, which is that direction. But do you remember what we said before? This one is pointed straight down at point A. That means it goes right through point A. There's no distance. So the distance is 0. So we get the same answer, 636 pound-feet counterclockwise. And the question then asks us one more thing, is which way will it rotate, clockwise or counterclockwise? Which one's bigger? That one is bigger. So your final answer there would be, it will rotate clockwise. Let's jump right into a 3D one because 3D is just so much harder with moments. This is a problem you can see in the picture. There's some kind of a rod. It's curved from C to A. And at point A, it has a force applied to the end, which goes along a rope that goes from A to B. And unlike other problems, we're not actually given F. We have to solve for F. And we're finding the F that would actually cause this curved rod to break right here at point C. And what that means is that we need a total moment of 80 pound-feet to be developed at C. That's probably based on the size of this bar and the material that it's made out of. So somehow we got to figure out how big of a force will give us a moment at point C of 80 pound-feet. So let's go through this really slowly. This is a difficult problem, but we can do it. Our main governing equation is moment is R cross F. I'm going to need a bunch of vectors to solve this problem. I'm going to need to get my force vector written as a vector. Start with a position vector from A to B, turn it into a unit vector so I can get that direction, and then multiply it by my unknown force so that I can write F as a vector. But I'm also going to need to get this position vector that goes from point C to anywhere I want to choose along that line of action. So I can either go from C to A for my position vector or from C to B. It won't matter. You'll get the exact same number out of the cross product. So let me write down those two position vectors and then we can decide which one we would like to use. So I wanted to just take the short one, go from C to A. There would be the position vector from C to A. To make this easier, why don't we write down the coordinates of these points? I think that'll make life easier. At C, we are located at 0, 0, 5. A is a little bit more complicated. Well, let's do B. B is easy. B is located at 6, 7, 0. Okay, so let's actually write down RCB because that's pretty easy. R from C to B, you have to take the endpoint minus the original point. So you end up with 6I plus 7J minus 5K. Just taking the 6, 7, and 0 and minusing the 0, 0, 5. So that's not too bad. Oh, and I want to write down what units this has. This has units of feet. That can help me remember that this is a position vector, not a unit vector. And it turns out in a moment equation, you need a position vector for R. But let's see if we can figure out where point A is. To do that, we're going to need to use a little triangle right here. That'll give me the Y and Z coordinates of point A. Let me draw that little green triangle down here. What it looks like from the picture is it's got a radius. This curved thing starts 5 feet up, goes along a curve, still 5 feet. So it looks like it's along a circular curve. So the hypotenuse of this triangle is 5 feet. And this angle up here is 60 degrees. So this little angle right there looks like it's going to be 30 degrees. So I have a 30, 60, 90 triangle, and I know the hypotenuse. So this side over here will be 5 feet sine 30, and this side down here will be 5 feet cosine 30. And now I know the coordinates of point A. Point A is located at 0 in the x. You have to go over 5 cosine 30 in the y, and finally up 5 sine 30 in the z. Gives me the coordinates of point A. So if I want to go from C to A, start at your end point and subtract your beginning point. So it's going to end up being 0 minus 0 is 0i. 0 minus 0 is 0i. For the j component, it's going to be plus 5 cosine 30j. And finally, for the k component, it's going to be plus 5 sine 30 minus 5k, which will end up being a negative number because 5 is bigger than 5 sine 30. And that also is all units of feet. We've got r from C to A. We've got r from C to B. I'm also going to write down r from A to B so that I can get the unit vector from A to B so I can get the force vector. So r from A to B, again, start with your end point, subtract your beginning point. It's going to be 6i. Then for the j component, it's going to be 7 minus 5 cosine 30j. And finally, 0 minus 5 sine 30k. That's all in units of feet as well. But I don't actually want to use AB as a position vector. I'm using that as an intermediate step to get the unit vector. To get the unit vector from A to B, I would need to divide this by the square root of the 6 squared, this guy squared, and that guy squared. I'm going to just do it all in one step because then finally, to get my force vector, it's going to be an unknown magnitude f times RAB, 6i plus 7 minus 5 cosine 30j minus 5 sine 30k. But then that has feet in it, so I got to divide the feet out. So divide it by its magnitude. 6 squared, 7 minus 5 cosine 30 squared, and minus 5 sine 30 squared. See what I just did there? I want a position vector when I'm finding the distance from C to the rope, or from C to the rope down here. So I'm going to keep one of these as a position vector when I plug it into my moment equation. But to write the force as a Cartesian vector, it's pointed in some funny direction. And I was able to get a position vector that has in it the direction, but also the length of that rope. So what I do is I write the position vector down, but then I divide by its length to create a little unit vector that when I multiply by my mysterious unknown force magnitude F, it will give me my force vector F written as a Cartesian vector. That comes out to be F times 0.8539i plus 0.3800j minus 0.3558k. Keeping quite a few decimal places there. I even keep more than that in my calculator when I do this. Then we're going to need to do a cross product. So I can pick, you actually can pick either of these that you want to do your cross product. Now, this one looks simpler because it doesn't have funny numbers like 5 cosine 30 in this, but it doesn't have a 0 in it. And it turns out in cross product, zeros are friends. So I actually want to use RCA when I go to do this because it has a 0, so it makes my cross product faster and easier. So RCA simplifies to 0i plus 4.330j minus 2.5k. Now we're ready to set up our cross product. The moment is r cross f. The way we write that down is we put an I, j, k across the top row. We put our position vector in x, which is going to be 0, 4.330 feet minus 2.5 feet. And then we put our force vector, 0.8539f, 0.3800f, and minus 0.3558f. Signs are crucial in here. And this is a great point to just double check. Plus, plus, minus, plus, plus, minus, and plus, plus, minus, plus, plus, minus. Because if you miss any of those negative signs, you're going to be in trouble. You can, at this point, use cofactor expansion if you're good at that. Cofactor expansion means you take the I and then you cross out the row and column that have the I in it and you do a determinant of those numbers. I don't actually recommend cofactor expansion unless you're already really good at it. And here's why. A lot of students, when they do it, they totally forget that with the J, you have to include a negative sign. And so many students leave that negative sign out that I think let's just do it a different way. So I'm going to show you my preferred way to evaluate these. You first take your first two columns, copy and paste them to the side. Now we're going to do what's called a basket weaving technique. I like to use colors to separate it. First, we're going to go downhill left to right, and we're going to add. Let me write those down. We're going to have an I times 4.330 feet times minus 0.3558 F. Then we do the next one, which is the J piece, of plus J times minus 2.5 feet times 0.8539 F. And finally, plus K times 0, here's where the 0 becomes our friend, times 0.3800 F. Next, we have to go the other direction. So we go downhill to the left, minus, minus, minus. Every time we draw one of these, we need to be able to multiply three things together. And that's why we wrote those other two columns down over here, so that we could go all the way across with 3. So our minus becomes a K times 4.330 feet times 0.8539 F. Then we have minus I times minus 2.5 feet times 0.3800 F. And finally, minus J times 0 times minus 0.358 F. Now those zeros are 0. We then need to combine I's, J's, and K's. So our moment as a vector ends up being, first I'm going to take the two I terms. This one ends up having a negative sign in it. This one, the minus minus, becomes a positive, and our X component becomes, when you combine those two, minus 0.591 F in the I direction. Now the J is just the single term right here because the other one had a 0 in it. So we end up with a minus 2.135 F in the J direction. And then for K, it's just this term, which is also negative, minus 3.698 F in the K direction. And it's whatever units F is times feet. The problem said that the rod will fail when M has a magnitude of 80 pounds-foot. Actually, it didn't say magnitude, but I'm guessing that's what it actually means. So we want the magnitude of M to be equal to 80 pound-feet. So let's find the magnitude of M. Well, that's the square root of all those things squared. So we end up with a minus 0.591 F that gets squared, a minus 2.135 F that gets squared, and a minus 3.698 F that gets squared, and the feet get squared and then square rooted, so that's multiplied by feet units. And simplifying, we get 4.310 F times feet, because all those numbers had feet associated with them. That all has to equal our 80 pound-feet. So the feet cancel, and we'll get an answer in pounds. So solving, we get that F equals 18.6 pounds. So what this means is that when F has a magnitude of 18.6 pounds, it will be just a big enough force that it will cause a moment about point C that has a magnitude of 80 pound-feet. The process is what I want you to focus on. We found coordinates of A, B, and C, and then we found some position vectors. One that went from C to A, one that went from C to B. We ended up just using the one from C to A because I suggested using the one with the 0 in it, but you could use this instead. Then we also found a position vector from A to B, not because we needed that in our moment equation, but because I needed a way to get the direction of F. So we use that position vector from A to B, divided it by its length to make a little unit vector in the direction of AB, then multiply it by our unknown force magnitude F to get an expression for our force as a Cartesian vector. Basically, we just need to know what are the relative sizes of the three components. Then we drop that all into a cross product. I showed you a new technique of using a basket weave technique to calculate and evaluate your cross product. We did that and we got the moment as a vector in terms of our unknown F. Then we found the magnitude, some of the squares square rooted, set that magnitude equal to the moment that we know will cause it to break, and solve for F. I have occasionally had a student not trust me that they could use RCA or RCB. Remember, we said we could either go from C to A or from C to B. And since it's not a bad idea to practice this cross product again, let's redo the math using RCB and make sure that we get the exact same thing. Cross product using RCB instead. Our moment is still an IJK across the top. Our R is now going to be 6 feet, 7 feet, minus 5 feet. And then we have 0.8539 F, 0.3800 F, and finally minus 0.3558. The basket weave says take the first two columns, copy, paste, and now to do the positive ones, we're going to go that way first. So we'll have an I times 7 feet times minus 0.3558 F. The next one is going to be plus J times minus 5 feet, 0.8539 F. And lastly is K times 6 feet times 0.3800 F. Now I've got to go the other direction. So I'll end up with a minus K times 7 feet times 0.8539 F minus I times minus 5 feet times 0.3800 F. Finally, minus J times 6 feet times minus 0.3558 F. And now nothing cancels because nothing is 0, so you have to do more math, but you can eventually get that the moment comes out to be, I have, I guess, a little rounding error somewhere, minus 0.592I, minus 2.134J, minus 3.698K. Those are all times F, and they're all times feet, which is the same answer as above. Finally, quick concept question to finish class today. So here is the concept question. What is the moment each force causes about 0.0? We've got 4 forces. So let's start with that 50 Newton force. What moment will it cause? Well, you can use the force times the perpendicular distance because the perpendicular distance is right there. The force is vertical, perpendicular distance will be 2 meters. So 50 newtons times 2 meters, that looks like 100 Newton meters. And the only other thing you have to figure out is it clockwise or counterclockwise? Think of your point as being this middle of the clock. So you put a clock face right there with, 12 at the top, 3, etc. So if you start at the middle of your clock and you have a force over here on the right going down, that is going to cause clockwise rotation. So this one is clockwise. 1 down, 3 to go. Let's do the 60 Newton force. Well, the moment is the force times the distance, but it's the perpendicular distance. So I have so many students that want to put in 4 meters because this point is 4 meters away, but that is not the perpendicular distance, right? Turns out this force is not going to tend to make the part rotate about 0.0 at all. It's just going to tend to pull it to the right because think of it as the force acts along a line of action that goes forever in that direction, and 0.0 is on its line of action. So the perpendicular distance is 0. So this one causes no moment. Let's do the 20 Newton force. It's 20 newtons. And now I need the perpendicular distance. You'll notice I've got a little dashed line along here. The 20 newtons lives along this line. So what I need is its perpendicular distance from 0.0, just from 0.0 to the line. Don't try to go all the way over here to where the force is. Go from O to the line of action. It's that vertical distance. So look at this little triangle. I have a nice 30, 60, 90 triangle with a 3 meter hypotenuse. It's this side I want. So if I use 3 meters times the sine of 30, I've got my answer. And it comes out to be 30 Newton meters. And clockwise or counterclockwise on this one. It's a little harder to see. So again, think of having a clock. The center is right there. There's my clock. This force is down at the bottom of the clock, pushing to the right. And if it helps you to extend those arrows forever, don't think of the forces just being all the way out here. It's along that entire line. It acts down here. It's going to tend to cause it to rotate that way, which is counterclockwise. The 40 Newton force. The moment is still force times perpendicular distance. So start with a force of 40 newtons. And now I need the perpendicular distance. So again, the force lives out here along this line that goes forever. So what I need is the distance from O all the way over there. So I need to go 2 meters plus 2 meters plus this side of my 30, 60, 90 triangle. So my distance is 4 meters plus 3 meters cosine 30. Solving that, you get 264 Newton meters. Shouldn't be surprising that this is our biggest moment. It is the force that is the farthest away by a lot. Now, will that one be clockwise or counterclockwise? So you come to the right on your clock and you're pushing down. So this one will also be clockwise. All right, that's it for moments.